Good morning, chemistry students. Here are your Chapter 3 Day 1 notes. We're going to be starting in your outline at scientific notation and going through percent error. So, again, this chapter might seem a little bit out of order, okay? It's because some of what is in this chapter you need to know to be able to do the chemistry and the math that's required in chemistry. So some of this should be review, I hope. Some of it will be new. But we're going to start by reviewing scientific notation, just to make sure that everybody's on the same page. When we're talking about scientific notation, so obviously we're going to be working in chemistry with some measurements. And in chemistry, a measurement is always going to be a quantity or amount that has both a number and a unit. So a measurement really never makes much sense without a unit. To say that something is 20, I don't know, 20 what? 20 feet? 20 miles? 20 kilometers? Okay, so again, pay attention in chemistry. Any kind of number you have always should have a unit on it. And in chemistry, we often work with very large and very small numbers. And because we're working with very small and very large numbers, we use scientific notation. So you should have learned about scientific notation at some point in your math classes, but just to kind of review. Scientific notation, when a number is given that way, a given number is written as the product. Remember, when we're doing a product, we're using multiplication of two numbers. And those two numbers are a coefficient and 10 raised to a power. Okay. So, for example, right, so this would be 6,328,932,000 meters. Okay, that's a big number. So this is a number that's easier oftentimes to write in scientific notation, and it would be 6.328,932 times 10 to the 9th meters. So remember up here we talked about a coefficient. Okay, this part here, this is my coefficient. And we also talked about the 10 being raised to a power or an exponent. This is my exponent. Okay, so again, you've learned scientific notation before. Remember coefficients, and this was on the ChemQuest that you did. Coefficients have to be a number equal to or greater than 1, but less than 10. Okay? So, in scientific notation, the coefficient is always a number greater than or equal to 1 and less than 10. The exponent is an integer. So keep in mind that a positive exponent indicates how many times the coefficient must be multiplied by 10. The other way to think about it is that it is the number of places that the original decimal point has been moved to the left. Positive exponents, remember, we're talking about large numbers. When we have a negative exponent, remember we're going to be talking about a small number. A negative exponent indicates how many times the coefficient must be divided by 10. We often usually think about this as the number of places the original decimal or the decimal has been moved to the right. Part of what's important to me is that you know how to put this in your calculator. So do you know how to put scientific notation in a calculator? For some reason, this seems to be something that sometimes math teachers haven't shown their students. So the way that you're going to want to do this is you're going to look for the E button. It's always a capital E. Sometimes it's a double capital E. So it sometimes is a capital E button. Okay. Sometimes it requires a shift. On the TI 30s, if you're using one of the recommended calculators, it's a shift. Okay. So, for example, and I really just want you to be able to put scientific notation in your calculator. If you have 8.0 times 10 to the negative second times 7.0 times 10 to the negative fifth, okay, you would put this in your calculator as 8e negative 2. So the E button, okay, takes the place of the times and the 10. Okay, so that means that you don't have to type that when you use that E button. Okay, and then you do your multiplication, 7e negative 5. So what I'd really like you to do is pull out your calculator, put this in your calculator, and see that you get the correct answer, which is 5.6 times 10 to the negative 6th. We're going to do one more. I'm going to kind of squeeze it in up here. 7.1 times 10 to the negative 2nd plus 5 times 10 to the negative 3rd. You're still going to put this in your calculator using that E button, so 7.1e negative 2 plus 5e negative 3. You should get 7.6 times 10 to the negative 2nd. On ChemQuest 5 or ChemQuest 7, and I think it was ChemQuest 5, I made a correction video using the document camera, and I have the calculator underneath there, and I show you how to enter this. So if you didn't for some reason watch that correction and you're not familiar with using this button, I would encourage you to take a look at those correction videos for ChemQuest 5 and ChemQuest 7. So scientific notation, the part of it that I just want to make sure you're comfortable with is that you recognize numbers with positive exponents are big numbers, numbers with negative exponents are small numbers, and that you know how to put scientific notation into the calculator you're using. So the next thing we want to kind of talk about is how we know how good our measurements have been. So this is we're going to talk about accuracy, precision, and error. And really what we're going to be talking about here is our correctness and our reproducibility. Okay. Relate to the concepts of accuracy and precision. Which are quite different. And here I'm going to say to chemists, but really it's to any kind of scientist. So kind of in our everyday use of these words, you might not really be very sure of what the difference between them are, because you probably think they sort of mean the same thing. However, to a scientist, accuracy and precision are very different things. So we're going to start by talking about accuracy. Accuracy is a measure of how close a measurement comes to the actual or true value of whatever is measured. So, accuracy, right, is correctness. Okay, so when we're talking about accuracy, we're really looking at our correctness of our measurement. This also means then that to evaluate the accuracy of a measurement. The measured value must be compared. Right? We have to be able to compare what we measure to what it's supposed to be. And in chemistry and in science, we have books that are full of known information about different elements and different substances. So, for example, if you are figuring out the boiling point of a substance, you can look in a book and probably also on the internet fairly accurately and find what the true boiling point of that substance is. And so you can compare the boiling point you measure to the boiling point that it really is supposed to be. Okay? So for accuracy, to be able to talk about how close or how correct we are, we have to be able to know what the true value of it is. Again, accuracy is not the same thing as precision. Okay, precision is a measure of how close a series of measurements are to one another. Irrespective of the actual value. So when we come back here, precision has to do with that reproducibility. Okay, and so when we're talking about precision, we're really talking about whether or not we get the same answer over and over. That's why, right, this word of a series is important. To talk about precision, you can't just make a measurement once. So if you kind of reflect back on your experiences in science and kind of doing labs and experiments up until this point, oftentimes, you've probably been asked to do something twice or 3 times. And that's because that was so that you could kind of verify that your precision, that you're consistently getting the same value. Now, what's important here is, notice, it doesn't matter what the actual value is. So it doesn't matter whether you get the correct answer or not. It's just a question of, did you every single time get the same value? To evaluate the precision of a measurement, you must compare the values of 2 or more repeated measurements. So again, this is this idea that you can't just do something once. Now, sometimes for practical reasons in a lab, ourselves, we don't necessarily do this multiple times, but if you share, like everybody in the class is doing the same experiment, if you share your data so that everybody in the class has your data, and you all were measuring the same thing, now you can talk about precision, right? Because you can talk about, as a class, how precise were you? Were you able to get the same answer over and over? Ideally, okay, you would do this yourself, okay, multiple times. But sometimes for time reasons, we do this by comparing or looking at our class data. So one of the nice ways to think about accuracy and precision is to think about targets. So this is like whether you want to think about it as an archery target or you want to think about it as a dart target, whichever you prefer. Okay, so again, I'm going to actually make this a little bit bigger. Okay, to talk about this, remember, we have to look at, okay, a series of measurements. So here's my target. Here's my bullseye, right? That's what I want. And these represent either my arrows or my darts. So, am I accurate? Am I precise? This demonstrates both good accuracy, and it's accurate because I hit the bullseye every time. It also shows good precision. Why? Because all 3 of my throws or my shots were in the bullseye. So that means that however I'm doing this, I'm doing it the same way every time. All right? Think for a moment then, what would my results look like if I had poor accuracy but good precision? Poor accuracy, good precision. Poor accuracy means I didn't hit the bullseye. But good precision means I'm still, my shots or my throws are tightly grouped. So they might look like this. This is poor accuracy, so I'm not accurate. But good precision. All right, lastly, what would my results look like if I had poor accuracy and poor precision? What would my results look like if I had poor accuracy and poor precision? Right? They'd be all over the place. They might even not hit the target. Right? So this is poor accuracy and poor precision. Now, ideally, in science, right, I want to be doing this when I do a lab. I want to be accurate and I also want to be precise. That's ideal, right? But oftentimes our labs don't go quite as we expect. So the next best thing is this, okay? Because at least here, I'm not accurate, but whatever I'm doing it the same way every time. Right? If this is archery or darts, right? Archery, I'm pulling back my bow, I'm aiming the same way every time. Darts, however, my positioning my body and my arm, I'm doing it the same way every time. I can help this person, right? I can say, hey, were you aiming here? But you hit here. So, hey, how about next time you try to aim down here? Because then it looks like your stuff will hit the bullseye. Right? It's easy for me to correct this person. I can kind of just say, aim slightly differently. Now, the problem is, right, this person over here, like, this is not what we ever want to be in lab. This person's all over the place. They're not accurate, and they're not even precise, which means every time they do this, they're doing it differently. It's very hard to help this person. Right? This would be me golfing. Okay? I'm not swinging the golf club the same way every time. I'm not going the same distance every time. It's a mess. Okay? This person is a mess. This person is maybe not even reading the directions correctly. Like, something's going on that they're not even consistently doing things the same way. Okay, so in science, right, ideally we want to be like this. But if we're not like that, then the next best thing is we want to be like this. Even if we don't get the right results, we want every single time we do our lab that we're getting at least the same results ourselves, even if that's not the results that we were supposed to get. So when we're talking about accuracy and precision, in labs, and especially, we often calculate something that's called a percent error. And to calculate a percent error, there's a couple things we have to know. We have to know what the accepted value is, which is sort of what it sounds like. This is the correct value for the measurement based on reliable references. Right? So there's this book called the CRC and the Handbook of Chemistry and Physics, and it has all kinds of information about all kinds of different substances. That's a reliable reference. Is Wikipedia a reliable reference? No, right? So again, this would mean that you're looking up what the correct value for whatever you measured is supposed to be. Experimental value, this is the value measured in the lab. So this would be, if you performed a lab, this would be the value that you got when you did the experiment. We use accepted value and experimental value to calculate our error. Error is defined as the difference. And remember, when we're talking about difference, we're going to be doing subtraction between the experimental value and the accepted value. So an equation for error is that error equals accepted value minus experimental value. That means that our error may be positive or negative, right? If it's positive, it means that our accepted value is larger than our experimental value. If it's negative, it means our accepted value is smaller than our experimental value. Really, all error tells us is it shows the amount by which our experimental value differs from our accepted value. So error is useful, but typically it's not what you'll be asked to calculate in a lab. Typically in a lab you're going to be asked to calculate percent error. Percent error is a relative error. It is the absolute value. Remember, absolute value means that you just take the positive value of whatever you have, of the error, divided by the accepted value, multiplied by 100%. So again, we have an equation for this. It is the absolute value of the error divided by the accepted value times 100%. Now, this isn't typically the equation most people remember. What most people remember as the percent error equation is that percent error equals the absolute value of the accepted value minus the experimental, which is how you calculate error, divided by the accepted value times 100%. So normally, this is the equation people remember for percent error. So we're gonna do an example. Thought I had given myself another little bit of space, but I guess not. So I'm gonna write the problem up here. The boiling point of pure water is measured to be 99.1 degrees Celsius. Calculate the percent error. So that's our problem. So the boiling point of pure water is measured to be 99.1 degrees Celsius. Calculate the percent error. So as we do this, right, first off, 99.1 degrees Celsius, that's our experimental value, right? Because that the key there being word being measured. So we know our equation, and I'm picky about this. I want to see my equation first, so always in kind of words or letters. Then I want you to plug in your numbers and units. Now, I don't have the accepted value here, but I want you to think about what you already know about water. Do you know the boiling point of water in degrees Celsius? I hope so, right? The boiling point of water in degrees Celsius is supposed to be 100. So absolute value of 100 degrees Celsius minus 99.1 degrees Celsius, which is my accepted value, or my experimental value, divided by 100 degrees Celsius times 100. Okay. And when you do that, you should get 0.9% error. So this is the work I expect. Problems on quizzes and tests will be worth 5 points. The 5 points will be broken up this way. You get 1 point for showing an equation. You get 1 point for showing your work. You get 1 point for your answer. You get 1 point for your units. In this case, our units are just percent. And after tomorrow, you're going to get 1 point for significant figures. So problems will always be worth 5 points. And if you don't show an equation like this, you're going to lose a point. So I'm giving you fair warning so you're not surprised. Your homework today is on page 53, exercise 3. You're going to answer that question. Have a good day. I'll talk to you tomorrow.